Good morning, everybody. Mr. Perez here. So we are into section 8.2.1. Today we're going to be working with similar figures, something we have worked with before. But then we're also going to talk about how the area changes with similar figures. One of the words that we use really often is scale factor. So that's the ratio of different dimensions in similar figures. So when I bring that up, just remember that is something that we've used in the past. So to start, we're going to go through this rowdy rodent example, like it says here, to celebrate the victory of your school's championship girls ice hockey team. The student body has decided to hang a giant flag with your school's mascot on the gym wall. Now, obviously, or I'm 99% sure we don't have a girls ice hockey team. We'll just pretend. And we're also going to pretend that our mascot is the Rowdy Rodents. But like it says, to help design the flag, your friend Archie has created a scale version of the flag measuring 1 foot wide and 1.5 feet tall. So that's this green flag right here. And so this is just a scale version, meaning that when we make the real or final version, it might be a different size, but the shape is going to be the same. So the first question that we have here, part A, is asking us if the student body thinks the final flag should be 3 feet tall, how wide would this enlarged flag be? So again, we have the dimensions for the scale flag, which is 1.5 feet tall and 1 foot wide. But if we actually look at the final version, so that'll be this one over here, they decided that it should be 3 feet tall instead. So as we look at this right here, the height is going to be 3 feet. So we don't really have to set up a ratio if we don't want, but if we made it look like that, if we took that 3 feet and put it over the 1.5 feet, it looks like the scale factor is 2, which means that this is 2 times as big. So if we know that, then when we work up here with our width, we know that this is going to be equal to 1 times that scale factor of 2, which means that it is 2 feet wide. So twice as tall, twice as wide. So I'll just write that down here for part A. Again, we're taking notes on this, so I'll have some more after this. But since we know that 3 feet over 1.5 feet needs to be the same as our new width, x, over 1, we can cross multiply here, and we get 3 equals 1.5x. When you divide by 1.5 and divide by 1.5, we get that the x is equal to 2 feet wide. So that's the answer to our first part. For part B, now it's asking us if Archie used $2 worth of cloth to create his scale model, how much will the cloth cost for the full-size flag? So it's asking us to discuss with the team. I will work through this with you instead. If we know that the flag is 2 times as big, you might think if it's 2 times as big, that means it's going to cost twice as much. But something actually changes because we're talking about area now. We're not just talking about the scale of one side. So when we think about the area, it's actually going to be a different number. And I have an example here. We'll pull this up right here. These are our 2 flags. One is the scale, this green one, and then we have the red one, which is the final one. So like it said in the example, one flag or one scale flag is equal to $2. That's how much one flag costs. When we look here, if I were to move this on top, let me bring this to the front. If this fits right here, and then I know that I need at least a couple more. Let me move this one up here. Looks like I've got 2 and 3, and then we've got a 4th one. So we've got 4 of these that fit inside. So since we know that there's 1, 2, 3, 4 flags, we know that we need 4 scale flags to make the final flag. So our cost is actually going to be that 4 times $2, which means that we're going to need $8 worth of cloth. So again, this idea of the length of a side compared to the area is a little bit of a different relationship, and we'll take some notes on that now. But even though the flag is twice as long, it's actually 4 times as expensive. So to show you one example of this, a little bit different of a shape, so let's think about 2 squares. So if we have 2 squares and one of them is, let's say, 2 feet in length, and the other one, let's say it is 8 feet in length. So since we know that with squares, all their sides are the same, that means this is going to be 2 feet, 2 feet, 2 feet. And all of these sides are going to be 8 feet, 8 feet, and 8 feet. So we have some dimensions for this square. If you look at it, when we think about the scale factor, we know that our scale factor here is going to be 8 over 2, which means that the larger square is 4 times as big. So when we think about perimeter now, we want to talk about perimeter and area. The perimeter of this flag, or of this, not flag, but square, is going to be 8 feet. We know that because we add up all the sides. And the perimeter of this is going to be 32 feet. But then when we think about the area of this square is 64 feet squared, and the area of this is equal to 4 feet squared. So we have these two areas and these two perimeters. Like I mentioned before, the scale factor is equal to 4, 8 over 2. If we think about the perimeter ratio, so the perimeter ratio is just taking our two perimeters and placing one on top of the other. That would be 32 feet over 8 feet. And it looks like that is also equal to 4. So now we know that the perimeter ratio and the scale factor are actually always going to be the same. The last one, though, when we think about the area ratio, those are the two green values. If we were to take those two and place one on top of the other, I'm using the large over the smaller one. You have to be consistent with which one you place. 64 feet squared over 4 feet squared. When I simplify that, we actually get 16. So even though the shape is 4 times as long, the area is actually 16 times as big. So these are the formal notes that I want you to take. We'll box this up in a second, but for similar figures, not just triangles and squares, but all of them, for similar figures, we know that the perimeter ratio, let's see, the perimeter ratio is always equal to the scale factor. So if one side length is twice as big, that means the perimeter ratio or the perimeter is also twice as big. But for the area ratio, that is actually always going to be equal to the scale factor squared. So these two equations are going to be very helpful later on in this chapter. That means that if the shape is twice as long, it's actually going to be 4 times as big. So as an example, these two, as you can see, are equal, 4 and 4. But the area ratio is equal to 4 squared. So that's that idea of the scale factor squared. So this right here, I would box it up, highlight it, whatever you would like to do, but make sure that you use this to your advantage a little bit later on. These notes are going to be really helpful for the quiz and for the test. We'll just kind of highlight that right there. So now that we have this is actually going to help us with our next example down here. So if we use this to work through these two examples, it looks like we're using perimeter as an example first. there's a little bit of information we have here, but we're looking for, as it says, the perimeter of the larger figure, figure B. So there's a couple things we do know. 2 to 6. That means that the figure B is 3 times as large. In other words, our scale factor is equal to 3. That also means, if you look back up here, that our perimeter ratio is going to be the same number. So our perimeter ratio is also equal to 3. So because we know that, we can actually figure out what our perimeter of the larger figure is. Let's just call this for now, let's call this perimeter x. So x over 27, which means the larger perimeter over the smaller perimeter, that should be equal to 3. We know that because the perimeter is 3 times as big. I'll put this over 1, and then it allows us to cross multiply, and we end up with x being equal to, and let's see, it would be 81 feet. 3 times 27 gives you 81. So the perimeter for the larger figure is 81, which is 3 times as big as 27, just how the side lengths are 3 times as long. As another example, if we're working with the area, and we don't know the area of, it looks like the smaller shape, but we do know the area of the larger shape and both dimensions of one side. So with these two figures, again, we know that 7 to 21, 3 times as big. Our scale factor is equal to 3. That does not mean our area ratio is equal to 3, though. Again, our area ratio is actually our scale factor squared. So when we figure out our area ratio, we need to take that 3 and square it. And when we do that, we get that our area ratio is equal to 9. That means that this larger figure is 9 times as much area as the smaller one. So when I take this 360 feet squared all over, let's call this x feet squared. So that's what this is going to be for us. Call that x. We know that equals 9 times as big. Putting that over 1 like before, and we cross multiply, we get 360. By the way, these feet squares will cancel out. 360 times 1 equals 9x. Simplify that. 360 equals 9x. And then we divide by 9 on both sides. That cancels out, and we get x is equal to 40. So we know that our area of the smaller shape is 40 feet squared. That is the area of our smaller shape. So I would use these two examples to work through the practice problem. Our practice problem is actually going to be from the CPM lesson as well. If you look here, it is problem 869, A, B, C, and D. So those are the 4 that you'll just continue on from here to work through as your assignment for today. If you have any other questions, please take advantage of office hours or shoot me an email, but hopefully that helps you work through this, and we will continue to get some practice with this later on this week. All right, have a good one.